Okay, so here we have the next question that we have on the menu today, and it is asking us about radio stations. So radio stations are usually identified by their frequency. When a radio station in the middle of the FM band has a frequency of 95.3 megahertz, the speed of light, and okay, so the speed of light, the name is kind of misleading. The speed of light is all electromagnetic radiation, and radio waves do count as electromagnetic radiation, so they will also move at the speed of light. So this is the speed of light, and we need to find out the wavelength of this speed. Of this radio station. Okay, cool. So let's look at our givens in this question. We are given our frequency is 95.3 megahertz. And that is actually a very reasonable number for a FM radio station. You've probably seen FM radio stations around like maybe from about 80 to like 120. Those are typically the frequency ranges that we'd expect. But we want to know that this is the same as 10 to the 6 megahertz. So we could rewrite this as 95.3 times 10 to the 6 hertz. It's not going to hurt you, but it might hurt you if you don't convert that mega into a number like this to just get the base SI, the base hertz. Okay, we generally want to convert all our prefixes. It makes life a lot easier. Okay, the second piece of information that we're given is the speed of light. So speed, we're going to use v. Maybe better be to say the velocity of light. It is given with high precision here, so we want to use everything that's given to us. 2.99792 times 10 to the 8 meters per second. Okay, now we are looking for the wavelength. This is our target. Okay, so the way that we want to address this question is with something beautiful called the universal wave equation. Universal wave equation. Okay, so essentially the universal wave equation is the velocity is equal to the frequency times the wavelength. Okay, yeah, it's actually it's fairly straightforward for this question. So we just have to isolate the lambda, which represents our wavelength, and well, that's just going to be lambda is equal to our velocity divided by our frequency. So let's do that math real fast. Let's sub in our numbers. 2.99792 times 10 to the 8 meters per second. And here we have 95.3 times 10 to the 6 hertz. Now, hertz is the same as saying 1 divided by seconds, or seconds inverse. So if you actually look at the units, they do cancel out just meters, which is very reasonable and what we'd expect. Okay, so I'm going to send this through my calculator and find out what type of numerical answer this is going to be. So with the maximum precision level, 2.99792 times 10 to the power of 8. Divide that whole thing by 95.3 times 10 to the power of 6 for megahertz. Do this calculation ASAP fast, and my calculation for lambda, our wavelength is 3.14577 meters, but we gotta worry about our significant figures. So we only have 3 significant figures that are available to us because of this a megahertz value. So let's convert this to 3 sig figs. So our lambda is going to be officially 3.15 meters. Now I know it's tempting to do 3.14 because everyone likes eating pie, but you know, if we're going to round this properly, it has to be rounded properly. So 3.15 is going to be our wavelength. Yeah, and we pretty much came to the same conclusion here. Just watch out for sig figs. So above solution is good. Good job. Cool.